This video will focus on what physics is and isn't. This section of the class is focused on how big distances Hello everyone. So this video will focus on what physics is and isn't. This section of the class is focused on distances, big and small. We are expanding on orders of magnitude, but this time putting distances into context. The way we measure distances depends very much on what we're measuring. If we're measuring the distance between the Earth and the Sun, we use an astronomical unit, or AU. 1 AU is the average distance between the Earth and the Sun. So it's about 93 million miles or 150 million kilometers. It's an average because the Earth's orbit is slightly elliptical, so the distance changes throughout the year. When we are asked about the nearest star and the nearest galaxy, we use a different unit, the light year. A light year is not a unit of time, it's a unit of distance. A light year is the distance light can travel in 1 year. Since light travels at about 186,000 miles per second, that number adds up to a staggering number. This is about 3 times 10 to the 8 meters per second. To give you some intuition, light from the moon takes about 1.3 seconds to reach the Earth. Light from the sun takes about 8 minutes to reach us. That means when you look at the sun, you are seeing it as if it was 8 minutes ago. When you look at the nearest star, you are seeing as it was 4 years ago. Here on Earth, we don't need such massive distances, so we use kilometers or miles, which fit our planet's scale. But we can also go to the other direction, into the very small. Here we can use prefixes like micro, nano, pico, milli. So milli is 10 to the minus 3, micro is 10 to the minus 6, nano is 10 to the minus 9, and pico is 10 to the minus 12 power. You've probably heard of nanotechnology. That simply means technology in the scale of a nanometer, or a billionth of a meter. So for example, modern computer chips work because we can create nano-sized transistors These are tiny switches, and they are the reason why your phone, laptop, and this video can exist. The transistor is arguably one of the most important inventions in human history. It has allowed technology to double in power every 2 to 3 years following Moore's law. Moore's law basically says that we can half the size of a transistor every 2 years. And this has allowed an exponential growth in technology since we've been able to essentially double the power of microchips, nanochips every 2 years. So think of it like fitting more and more tiny switches into the same space. Every time we shrink them, our technology leaps forward. Biology also uses small scales. Cells are measured in microns, while DNA is measured in nanometers. Physics, chemistry, biology all depend on scale, and understanding these units connects the science together. Now let's think about something fun, the idea of cosmic address. We all know our street address here on Earth, but what if you wrote your address in the universe? It might look something like this. You'll have your street address, city, you'll have your state, you'll have Earth, or USA, perhaps your country, Earth, and you'll have the solar system, our specific solar system. We live in the Milky Way galaxy. And the Milky Way galaxy is part of a local group of galaxies. And the last, and maybe the most important, is the universe. So, our cosmic address is pretty complex, right? So, if you meet an alien, this is what you would tell them where you live. So this shows that distances don't just measure things, they also place us in a larger cosmic neighborhood. That way, you'll see both the number and the perspective. And together, they'll remind us just how vast and connected our universe really is. But before we close, let me add something important. Sometimes people say everything is physics. That's just simply not true. Physics is powerful, but it doesn't replace the other sciences. Physics gives us mechanics, electromagnetism, quantum mechanics, thermodynamics, to name a few. Yeah, let me write these on the board. Mechanics, E&M, electromagnetism, quantum mechanics, and thermal. These principles influence chemistry, biology, and even astronomy, but physics alone cannot explain a chemical reaction. It cannot tell you how DNA copies itself inside a cell. Chemistry has its own tools to understand matter and reactions. Biology has its own methods to study living systems. Each subject complements the others. They are essential and non-substitutable. Sometimes sciences build on each other, but each is different and solves a different layer of reality, solves a different problem, explores a different layer of reality. Think of science like a building, like building a house. Physics lays the foundation, chemistry builds the walls, biology makes it a living home. Without one, the whole structure is incomplete. Together, they give us the full picture of the universe. That's the big idea for today. Distances help us measure our place in the cosmic to the microscopic. And the sciences working together help us understand it, not as rivals, but as partners in the great quest for knowledge. So a quick recap for today. Today we talked about distances on every scale, from cosmic to microscopic. We learned that 1 AU for astronomical unit, is the average distance between the Earth and the Sun. We also explored the light year, a unit of distance, not time. We saw how light from the moon takes about 1.3 seconds to reach us, and the light from the sun takes about 8 minutes. We also looked at smaller scales, nano and micro, and how they connect to technology. Transistors at the nanometer scale makes modern electronics possible. Finally, we discussed how physics connects with other sciences, but physics cannot replace chemistry or biology. Each science has its own essential tools and questions. Together, they build the full picture of reality. So whenever you think about distances, big or small, remember your cosmic address. And remember that science works best when all of its branches work together. Thank you.